G'day everyone and welcome back to my channel. Right, so we're going to get started on compensating the op amps in this thing. Well, the ones that need it anyway. Now, I've had a little bit of a look over it. Not testing wise, but tracing the circuitry out. And I can tell you now, a lot of the op amps in here are in an open loop configuration. So this is going to haunt me a little bit because when op amps are in a closed loop configuration, almost you can swap it out with another op amp as long as it's, you know, in the same specifications in terms of, you know, like what sort of voltages you can put in its inputs in comparison to its rails and all that sort of stuff, its bandwidth, current, whatever your specifications are, right? Slew rate, all that sort of stuff. But when you change one that's in open loop, you can run into trouble because if the older part's a slower part, or it has less gain, or it's a slower part and it has less gain, and then you put a newer part in that's got more gain, open loop gain that is, obviously, open loop gain and a higher slew rate and higher response times and all that, you know, you can end up with problems, which is what we got here. And like I said, most of the op amps in here appear to be in an open loop sort of fashion, so that's going to be fun. Could be a few to sort out. There are 8 in here in total. Yes. So, it's not all bad. Yes, I know. This is just bullshit for now. It's good enough. Just want to get a rough idea. Once we knock out oscillations and we start getting signals down to very, very small levels, we'll start using probes like this that I've customized that are even better than using this with, say, a spring like that. But for now, just to get started to see where things are, we'll be using the ground clip. Right, anyways. So, the outputs are actually reasonably quiet, which is good. That was the last time I looked at it. Thought so. It's just because I got the power supply turned up to 30 volts. The scope's on AC coupling. It's just taken a while for the capacitor to charge up in there. But as you can see, 240, 220-ish microvolts RMS, 2.6, 2.8, we'll call it 2.7 millivolts peak to peak. And it's the same on both sides, I've already measured that. So that's good. Just a quick look at the references, they're both the same. I've already checked. What I'm showing you now is what I've already checked. I've not checked where I need to be checking it, and we'll get into that, why that's going to be a pain in the ass in a second. So the reference, as you can see, is nice and quiet as well. All of them are pretty well the same. The capacitors, the bulk capacitors for all the circuitry on these boards, not necessarily a problem. That's quite normal. That is literally at the start of a circuit. So there will be additional smoothing after that and regulation and stuff like that. Let's have a look at this one. Yeah, see, that's already one capacitor further away from the first one. You see what I'm saying? capacitor goes into a resistor and into another capacitor, and it's already smaller. So that's all looking normal. So I'm already happy with the output on this thing with no load on it. And I'm happy with the power rails, I'm happy with the references. Obviously that's not what we need to look at, but what we need to look at is we need to start obviously at the first two op amps that are looking at the voltage and the current, and move our way up from there, because if there's any oscillation in the first two op amps, it's only going to come out of them and go into the next ones up the line, and everything's just going to be ringing. The problem with that, as you all know, is you can't really get access to much in here. So I'm going to have to come up with some very interesting ideas. The annoying thing about this sort of thing is, because we're looking at small signals, we need signal integrity. So we can't just go soldering on long wires and using, stuff like this. So we need to get right in there, and it's almost inaccessible. So it's going to be interesting, I can say that. I've still got a pain in my mouth. I've just come in here tonight just to get a start on this video. I guess we're going to look into most of everything tomorrow, but for you guys it will be the same day because it will be in the same video. But just to give you a bit of metal in there, just to give you an idea. The op amps that we want to look at first are on this lower board here, and we need to get underneath it with the thing powering on. And I've already sussed out, like if there's any viable options for it. I thought about, turning the edge connectors around. The power connector you can obviously turn around the other way, that's not a problem. I wouldn't be surprised if this is actually symmetrical and you can turn it around either way anyway. If you look at the way the board's laid out, it probably is. Oh, no, it probably isn't. Could be, but I'm not going to take my chances on it unless I was to trace it out. Anyhow, that's not the problem. We can turn that around. The thing is, wait, I might actually be able to do this without putting too much strain on the wires. Hey, you know what, guys? We might have this. Oh, wait, what am I doing? Trying to put the board in the right way. No, we want the board upside down. You know what? This is going to work. Well, that has saved a lot of problems. And this connector goes this way now. Okay, so now I just need a way of holding the board up so it can't touch anything. And I'm going to need to put some stuff under it because I need to be able to press down on it pretty hard with, the probe tip to get into places when I start doing compensation work. That's why I make these probes up. Basically, I take these normal probes, and you can see what I do. I chop off as much tip as I can to get rid of tip capacitance, and then I insulate everything with heat shrink, and just have this so I can just solder straight across something. It gives me really, really good signal integrity. Better than you can get with just this and a spring on the tip of it. And also, obviously, the advantage of that is I can just solder it across, say, the midpoint rail of an op amp and its output, and just leave it sitting there whilst I put in and out different RC values on a snubber or something and watch my waveform live. So that's why I do that. Yeah, I got a lot of custom stuff that I kind of customized to help me work my own way. I'll end up doing videos on some stuff like that. Yeah, okay, I'm just going to pause the camera for a minute and work out how I'm going to prop this up. I'm pretty much just going to have it sitting like that somehow. I'm just going to make sure that nothing here on this end can touch these panel connections on the back of the panel meter, and over here where the standoffs are, that can't short out to anything. So I mean, that problem's easy to fix. Right, and there's got to be something in here I can think of to use. We just need like a prop. Actually, you know what? I've got the perfect object. Oh no, that's too big. Yes. This plastic container, box, whatever it is. I have to take this connector back off just to get the board up. Alright, what are we resting on? Resistors, capacitors. Cool. I'm happy with that. That can't hurt anything. You know, I really got lucky there. I didn't think this was going to be viable. I was getting worried that I was going to have to take the boards apart and actually solder wires between the two boards and run them on my desk. Yeah, I'm pretty happy with that. No, that's still a problem. Come on. Okay, I can do it like that. I'm just gonna have to be gentle. If I put too much pressure on it, I risk bending a power resistor over, and that could possibly push its leg into something and short it. I don't think so. It looks like it can't, but yeah, I think we've got our board placement sorted. Yeah, cool. All right, let me just make sure. Yes, that power connector's turned around. Good. All right, so now we can turn it back on. Yep, it's working. That's good. I didn't think that was going to happen that quick, to be honest with you guys. That's really good. All right, well, let me go and just trace the inputs out again and just put some marks over what things are on the board, because I washed everything off when I cleaned the boards up. Some marks are still there on the other side, but I don't really know what anything is on the back here. I know one of these op amps is looking at current, one's looking at voltage. Same on the other side. I know they go into an OR gate. I know there's a reference up here that's compared against something that's divided down by a resistive divider, and the output of that op amp goes to a transistor, which then buggers off somewhere else. But that's literally all I know just from looking at the back of the board here. So I'm going to go off and trace a few things out, and then it'll be a lot easier for us to know what we're looking at. Because right now, all I can do is have a look at the inputs of my op amps, which I ain't going to do that quickly anyway, because I'm curious and it's here, so why not? I probably still got my scope turned up to like 5 volts at division, don't I? See? So there's some interesting stuff on that op amp. Yeah, I'm going to have to solder cables on here. Okay, but this is good. This is what I was imagining. I'm pretty sure that's the current one. Let's have a look at voltage. See, there's nothing on the voltage one, really. Oh, no, there is. It's actually quite a bit. Wow. That's just a sine wave, but I'm more concerned about this nasty looking waveform on the inputs of the current op amp. These two op amps are in open loop. They're just... Yeah, I'm going to have to solder. This is why I have these. Very handy. I got a couple of them already made up, so that's good. I'll just pause the camera for a second whilst I turn this off and warm my soldering iron up. Alright, that's a lot better. I'm just trying to look and see which op amp that is. Oh, man. I think I'm going to have to trace everything out. I'm pretty sure that is the current one. Yes. So when the current's turned all the way down, I'm noticing, oh, I don't know if it's coming out on camera. Is there that negative going spike that goes a lot further down than it goes up there? I notice when I turn the current down, it's present. When I turn it back up, you see it disappears. I don't know if that shows on camera for you guys. Yeah, no, it doesn't. Also, the supply's in the way. Sorry about that. Right, well, pretty high speed stuff. I mean, I was expecting it was going to be pretty high speed, and I'll tell you why. Because, well, it's in open loop configuration, and also the offset voltages that I'm noticing on this is like just how do I explain it? Offset voltages are going up and down on their own very slightly, and that's usually indicative of a high frequency oscillation. And usually the reason why an op amp going into oscillation or having oscillation on it causes the output to shift up or down is because the oscillation usually has more positive going parts to it or more negative going parts to it. It's like an asymmetrical waveform. Not asymmetrical. What's the word? Yeah, asymmetrical. It's not symmetrical. I think that's the right word. Anyway, you know what I'm trying to say. So what that does is basically it causes an offset voltage inside the diff pairs, inside the op amp's different stages, and that presents itself on the output. And as the oscillation changes, obviously the offset voltage changes, and that was one of the first things on. Look, my mouth is still swollen, so it's kind of hard for me to talk. That's another reason I'm not doing too much on this tonight. That was one of the first things I noticed once I'd pretty much got it all back together and where it is now. The slave channel, like I said, when you put it in and out of auto tracking and independent mode, the voltage never comes back to exactly the same spot. It'll be 30.01, 30.25, 30.50, 29.78. It's as if every time you flip that switch, the oscillation, how do I explain this, starts back up in a different form. Or it has a different effect anyway. So we know we've got these nasty looking spikes here. Incidentally, that's just the inputs we're looking at. Like I said, I haven't traced this thing out yet, so I don't know if they're I don't know how they're doing what in here. I don't know if things are being referenced to a sort of a halfway point in between the rails, if things are referenced more to the negative rail, if things are more referenced to the positive rail. Yeah, there's still a lot that I've got to trace out. But what I will do now, just quickly, just because we've got the positive rail right here and the output right here, we'll just have a look in between one of the power rails and the output and see what's going on there. I'd imagine it's going to be fairly much the same wave between both the power rails and the output, so have a quick look whilst we're here. So about 2.4 millivolts RMS, and the waveform that you see there, that's what's coming out of the constant current. I think it's the constant current monitoring one. Oh no, that's the voltage one. Wow, there you go. So that's the op amp that's monitoring the output voltage against, I don't know what, I haven't traced it out yet. Like I said, the circuit in this thing is kind of weird. It loops around the place. I mean, I would have imagined that the first op amp would be comparing the voltage against a reference voltage. It doesn't appear to be doing that. It appears to be comparing the voltage against, it appears to be comparing a divided down voltage of the output voltage against another divided down voltage of, I think, just the power supply, and then it compares that against the reference later on. I don't know what it's doing. Honestly, I've looked for the schematics for this thing, and I haven't found them anywhere, and I haven't taken the time to fully reverse engineer the thing. And I'm not going to either. I mean, I'll have a look at the op amps from the start and try and compensate them, and if that gets the problem solved, then I'm not going to look into it any further. If it doesn't, then yeah, I might have to sit there, pull the two boards apart, trace everything out, draw it out on the sheet so it makes sense to me and I can actually see what's going on. We'll just have to see, you know. But I should be alright. I should be alright. Alright, well, let's have a look on the one that monitors the current. I've got to remember to put clamping on these op amps too. That's something I want to add to them, because they're JFET input op amps. Huh. Oh. What? I've got to see that again. Oh man. Alright. Oh goodness. Wow. Wow, and that's interesting because, you know, when I put a load on it, how it only has that oscillation problem when the voltage is at a certain spot right down the bottom, and then you put a load on it and it goes crazy, tries to spit out like 12 amps. Right around that exact area on the pot is where it does that. And no, that's not the pot, that's the circuit. It just does that around that resistance area. That's just really interesting. The waveform going up and down, that's completely normal because I'm turning the voltage up, so it's just throwing offset off and my scope's constantly trying to reset it. But the waveform that you see there, that's, yeah. It's got a lot of stuff riding on it too. That's a very messy wave. That's got a lot of stuff riding on it. So there you go. I'd imagine the other side's going to be pretty well the same. I'm not going to even bother moving this to the other side until I've traced all this out and I know exactly what's going on. I'm not going to waste you guys' time, or my own time doing that, because it would just be pointless. Alright, well, I'm going to leave this for here. I'm going to go off to bed now, because it is late, but I just wanted to get a start on this, work out how I was going to get to it. Basically what I was going to do tonight is, if I couldn't get this flipped upside down, I was going to make it up on my bench so that I could get access to everything, but it seems that we have plenty of access. So I guess tomorrow morning what I'll do is I'll get up, I'll trace everything out, and then I'll just mark on the back of the board just some basic things, you know, like where the sampled down, divided down voltage from the input. Oh, why do I keep saying input? Output. I'm getting tired. Where that comes from, where the reference comes from, you know, which op amps for current, which ones for voltage, all that sort of stuff. I'm going to have to work out a few other things too. I'm going to have to look at the data sheets, because something else that could be happening, I noticed, like actually you guys already have seen this, the panel meters, when they're on amps mode, the needle goes up to 0.8 of an amp, and then as soon as it gets over 0.8 of an amp, it sort of like goes up to 4 and then kicks back all of a sudden, and then just sits around there. I think that's just an op amp in oscillation, but it also could be that the op amp's being used outside its input voltage specifications. I haven't actually measured any of the voltage differences between the positive and negative pins, and between the pins and each rail, and compared that to what the data sheet says that these op amps can take. I don't know 100% that these op amps are even running inside their allowed conditions. So yeah, we'll go over all of that tomorrow. I might even just upload this video for now, just so everyone's got a bit of an understanding of what's coming. I don't know, we'll see. But I'm gonna leave it here for now anyway, because it's 1:29 in the morning, and I'm gonna go get some sleep. But yeah, we'll be back soon. Alright, I've just I've just zoomed in the camera just so you guys can see what I'm looking at, because I've got the phone off on a funny angle. Oh, what the hell? Sorry. Where's my zoom gone? There you go. Right. You guys still can't see much, eh? That'll do. At least I can show you what I'm trying to show you. I just thought I'd quickly, because I can't see a TL072, which is probably going to surpass the old LM301 in every way possible, to be outside of any specs, but I thought I'd just check anyway. And no, it's not. It looks perfectly fine to me. This is the LM301, and I was just having a look at a few different things, like its input. Wait, where is it on this data sheet? I know we're not going to have any trouble, because on the TL072, sorry, let me just find, there we go, signal input pins, common mode voltage, VCC minus, plus 0.5 of a volt, and VCC positive plus 0.5 of a volt, differential voltage, voltage supply plus 0.2 of a volt, current minus 10 to plus 10 milliamps. That's never going to happen in here. Supply voltage, it's under that, it's running on 20 volts. So then I thought, all right, output swing, because this is where we could start running into problems, because it's only running at 20 volts. What's the output swing expected? So let's have a look. God, I hate this data sheet. Alright, should be here somewhere. Voltage, output swing from rail, here we go. Okay, so it goes to within millivolts, say a volt away from the negative rail, and it can get up to a volt from the positive rail. But that's with quite a heavy load and a huge supply voltage. So, no, we're not going to run into problems there either. Open loop output impedance. I wonder if that's specified for the LM301. I couldn't actually find anything so far open loop wise in the data sheets. Yeah, no. I was hoping to find open loop gain, but... Oh, it's right here. Here we go. 120, 115, 120 dB. Typical, yeah, okay. 120 dB. VS 40 volts. 2 kilo ohm load. Okay. Well, I don't know how to work out the open loop gain of an op amp without, like, just, I'm sure there's some maths you can do on other figures from the data sheet to work it out, but I'm certainly not that smart. Oh, open loop frequency response. Do we have any more open loop stuff? We've got voltage gain over frequency. Oops. I might just put my data on and just Google what the open loop gain is of an LM301 and see if I can find it out. Alright, I've been scrolling up and down Google for a bit and I cannot find anything. Furthermore, when I look at the TL072 data sheet, I don't even see anything here about the frequency. Oh, bloody hell. About the frequency range. That's in, so it's still kind of useless to me. Let's have a look at the gain bandwidth product of the LM301. That has to be there. Really? Man, people must have had to do a lot of maths back in the day. Like, we're so lucky now. Yeah, wow. I guess you have to work it out yourself. I really am going to have to sit down and have a read. Oh well. That's what I'm interested in, is just the open loop gain differences between the two op amps. Other than that, it looks like voltage wise I don't have to worry about anything to do with the inputs or output swing, so we should be good there. Yeah, cool. So it looks like we're just going to be doing compensation stuff. I don't think we're going to have too many problems. Why did I just close that? But I really do want to know what the open loop gain is on the 301 and what sort of frequency range that's in. And, you know, I want to be able to compare it against the TL072. I guess I need to learn how to, what do you call it? How to calculate that figure out of less information, which I don't know how to. So I guess I'm going to be doing some learning. Anyway, that's it for now. Okay, so I was just having another look over the LM301 data sheet, and I just found this here, large signal voltage gain. So it's actually in volts per millivolt, but it's 160. So back to the TL072. I guess I'm going to have to convert that to dB. One thing you guys will get to know about me is I am very, very smart, and I'm also very, very stupid. Let me explain. My maths is absolute dog shit. Where I might understand what every single one of these things does and means, when it comes to doing the calculations, I rely on calculators. My maths is dog shit, seriously. So I'm going to go and do the calculations between whatever that was. I think it was 160 millivolts. A volt or something, I can't remember. Yeah, 160 volts, millivolt. I'll go do the maths on that. This is what I mean about the cats getting into the box of wire. Anyways, I'll go work out what that is. 160 volts, a millivolt, and then I'll convert that to dB, if I can work out how to do that, and then see what it is compared to this. What are the conditions? There's 40 volts, VCC negative, plus 2.5 volts, oh, less than plus 2.5 volts, VCM, less than VCC, positive minus 1.5 volts. Let me just see. Oh yeah, it's not spec'd the same way. Fair enough. Although I tell you what, we do plus minus 15 volts. Look, we got plus minus 10 volts. We got 20 volts across our TL072, so it's not far off. So that figured pretty close. Doesn't seem to vary that much. I'm looking at the totally wrong thing. How on earth was I looking at that? Right. Stop it! I can't concentrate. Okay. So one's got a specified load, the other one doesn't. I guess that's just because the open loop gain drops with load. That's just my guess. But alright, so I'm just gonna pause the video. Oh, that's alright. I'll do it on camera. You got it. I can't win. Can't win. No. Oh, fuck. No, let go. Sorry. I'm sorry. You're not allowed up here. They're so sweet. Right. That's not what the video's about. And I've got another one sitting here on my chair sleeping. Anyways, mobile hotspot, come on. I'm recording a video. I'm just putting the mobile hotspot on my phone so I can put internet on this computer because I don't have internet hooked up to this computer in my lab at the moment. Come on. Auto connect, damn ya. Now you'll do it. Alright. So I'm going to ask Google, yeah, how can I even ask this? Oh, what was that? Was it in DBM, DBV, DB, DB? Yep, it's in decibels. Okay, to DB. I don't know if this is going to return anything useful for me, but let's see. Okay, I know that. I need to know how to do the math. It's in dBm. I'm already not someone who's good at dBs. I think 1 dB is equivalent to 1 point something volts or 2 point something volts. Yeah. So this is already going over my head. Decibels to voltage gain / loss to decibels. Okay. I think I might have found it. So, what have I got here? I keep losing where I'm at. Sorry, guys. Here it is. 160 volts per millivolt. Does that work like that? Is that how you type it? Yeah. Okay. I'll work this out in my own time so I don't bore the shit out of you guys, but basically all I want to do, now I know that the inputs and the outputs are within their constraints, not outside of limits. I just basically want to make sure the open loop gain's not massively over what the LM301 is. And if it is, we might have to do something about that. But other than that, I'm going straight into compensation. I just wanted to have a look at those two things first. So I'll go do the math on this. If anyone's got any tips for me, like a quicker way to do calculation between that spec there, large signal voltage gain or DC voltage gain, or whatever you want to call it, 160 volts millivolt. How can I convert that to dB? Not dBm or anything else, just dB. That will make it the easiest for me to wrap my brain around it and see the difference between the two in open loop. I guess once I've answered that question, we're literally just going to start compensating. Unless we have to knock some gain off of a few op amps. We'll do that first, obviously, but yeah. Alright. If anyone's got some tips for how I can do these calculations without having to do a crap ton of math, because like I said, math's something I'm not good at. It won't be hard for you to explain it to me because I understand what all these terms are. I just don't understand a lot of the calculations I have to do. I understand what things mean too. Like I know what delta means and all that sort of stuff. It's just more like my maths brain, like when it comes to actually dividing stuff, multiplying stuff, the square root of something, all that sort of stuff. I'm not good at working that sort of stuff out. And when I have to do complicated formulas, like when I design a switch mode power supply, I'm not going to lie, I sit there with a calculator and stuff like this, like rapid tables, and I'll use stuff like this Just my maths is dog shit. I use calculators for everything. I won't lie. Doesn't, like I said, doesn't mean I don't know the formulas or some of the basic formulas or what the parameters are, but when it comes to calculating it, it takes me a long time. So if anyone's got some tips on calculating stuff like this and some easier ways of doing it, let me know. I'd be interested to know. But yeah, I'll leave that for here. I'll go work out how I can calculate this, and if I'm happy with the results I see, we'll just get straight into compensation. If not, I don't even know. I haven't even considered what this could mean. You know, it might mean that I need to put some insanely high resistance, like a fucking giga-ohm or something like that, from the output to the negative input to knock down some gain. I don't know. Like, I really don't know until I find out how different the open loop conditions are between these two op amps and the given frequency range that's measured under too. That's something else I don't get with this data sheet. Not the TL072 data sheet. It's got everything on there. Open loop voltage gain, because it has its, because this data sheet, see, it's got its gain bandwidth product, it's got its slew rate, you know, I'm pretty sure I found every measurement in this data sheet that I would need to calculate all that stuff. But in the LM301 data sheet, it might just be me, like I said. It's probably just there are formulas that you can do, like using these bits of data to arrive at the answers that you need, but I don't know what they are. So, like, I don't understand how to work out the gain bandwidth product of this amplifier. I don't understand how to calculate the open loop gain in dB. There's a few things that I need to wrap my head around. These older data sheets that don't have as much stuff on them are quite hard for me. I'm a lot more familiar with stuff like this where everything's explained for you, you know? And they usually give you a few different conditions that they measure things under, which give you a bit of a tip too as to what it's going to do. Like, sometimes you'll scroll down from one table, and like this table says it's from 4.5 volts to 40 volts. You might get another table that's all just spec'd at 5 volts or something like that, you know? Like, newer data sheets just have a lot more information in them than older ones. So I might even just leave this video here, and then I can get some feedback from you guys, because that's all that's in this data sheet. As you can see, you got the absolute maximum ratings, and then electrical characteristics is literally just that. And if I want to work out anything more than that, I guess I have to study graphs. Oh, this stuff down the bottom is just for compensating them because they don't have internal compensation. But yeah. So basically, if anyone knows how I can calculate the gain bandwidth product of this, the slew rate, the whatever you want to call it, large signal voltage gain, DC voltage current gain, whatever it's called, whatever you want to call it, yeah, how I can convert that, or how I can get half of those figures that aren't there, and how I can convert also, like I was saying, that open loop gain into dB. Those are my 2 questions, 3 questions. Anyways, I'll sign off here, and I guess we will just start solving stuff and compensating. But this is the bit that's going to be the hardest for me to wrap my brain around. Compensation's nothing for me. I'll just calculate the frequency it's oscillating at, work out some ballpark figures, hook up the scope probe to it, and then just start adjusting the figures until it's right, you know. Obviously on the edge of, you know, slowing down response and dampening out oscillations and stuff like that, you know. There's always trade-offs, but anyway, that's not the bit that's going to be tricky for me. The bit that's going to be tricky for me is trying to work out if the op amps I've put in there are going to be doing funny things like trying to swing to their rails or whatever because of, you know, wildly different specs like open loop gain and stuff like that. So yeah. All right, I'm going to leave this here. I'll see you in the next one. Sorry, I just wanted to add something to this video before I sign off. I mentioned this the other day and I only just realised I actually haven't done it yet. And on top of what I'm about to mention, there was one other thing that I'm going to do. And I'm obviously going to do this before compensating it because both the things I'm going to do to it will knock out a lot of problems, especially with power rails to certain things like op amps and the constant current circuitry. So let me explain. These two 1 ohm resistors are what are used as the 1 amp current shunt. They used to have 3 wire wound resistors in there, so I put carbon film ones in there to lower the inductance and moved them up to 10 watts to these cats, I can't ever concentrate. Can you stop? To get a better tempo and less drift, or drift over a longer period of time, because obviously it's a bigger package, it takes longer to warm up, so you get what I'm saying. What we're going to do is we're going to make 2 symmetrical snubbers. By symmetrical snubber I mean instead of just having a resistor and a capacitor in series, what you have is you have a resistor on each side of the capacitor. So just imagine the 2 resistors hooked up to the 0.1 mono cap there, like so, and then these 2 remaining ends will go over each shunt resistor. Alright, so I'm going to put those in, those little snubber networks for the shunt resistors, because that was something I meant to do when I wanted to make the shunts like a order of magnitude better than what they were. Like, I'm not going to the point of making it out of a like Constantine wire, because it's 1 ohm. You'd have to use so much wire, you'd end up with so much inductance to it, it'd just defeat the purpose, right? And also if I wanted to put some small value thing like a 0.050 ohm shunt in there, I'd have to use like OP07 CP op amps at least, you know, or for the current sensing. Which is actually, I'm not going to lie, it's actually something I've actually been thinking about doing. Like the rest of everything, all the other op amps are just comparing voltages basically that are, you know, in the volts region, millivolts region. The TL072s are fine for that. But I was considering replacing those 1 ohm resistors with like a 0.1 or a 050 actual shunt, and putting OP07 CP op amps on the current detection, because I can get awesome tempo because I can use a proper shunt then. So I don't know if you've noticed in other videos, when I load a full amp on it, you see it's, oh god, my cats are fighting. Stop! I don't have time for this. You see the current go down as the resistor warms up, and that's going from a 3 to a 10 watt resistor, and it's still, you know, it still drifts. So I wouldn't mind doing that, but for now, look, for now, I don't want to keep this series going on too long. That'll be future mods. So for now, I'm just going to put those snubbers across the 1 ohm resistors, and that'll be that. The other thing I was going to do, I don't know how I forgot to do this already, because it's actually something I meant to do from the very get-go, and I did half of it. So there's no voltage regulators on here. There isn't even 2 transistor Zener regulators. Everything's just powered directly from Zeners. So some of the like this was just atrocious. They literally had how do I explain this? The ends of those 2 Zeners going down to 2 traces that then go to, or was it these 2 op amps? Yeah, those 2 op amps. And they had a 10 nanofarad capacitor on the output of the Zeners. I'm sure everyone that knows a little bit about Zeners know that they make quite a bit of noise, and a 10 nanofarad capacitor is not exactly going to shunt that out. So I've added capacitors to smooth out Zener noise. But the thing is, I noticed I must have been rushing because I didn't do it to all of the Zeners. I did it to the ones that power the op amps, but I forgot about the ones that power the references. And when I had a look at the references, the RMS value was small, but the peak to peak was a couple of millivolts. And you could see the waveform had a lot of stuff riding on it, a lot of high frequency noise. And I'd waged my bet that that's Zener noise because I didn't filter the rest of the Zener supplies. I was considering going the full Monty, and I think that'll be a future upgrade. Like the 2 future upgrades I'll end up doing to this is all the Zener supplies will get torn out and replaced with voltage regulators. And what I was saying about the current shunts and the OPO7 CPs, I'll probably end up doing that in the future, and then it'll be, you know, a really nice supply. But anyways, I digress. I'm going to put these snubbers in, and all the Zeners that power stuff that aren't filtered, I'm going to filter. And on top of that, the ones that I have already filtered, the ones I've filtered that have got some capacitor, like some electrodes and some monolithics, I think what I'm going to do, just due to the fact that this circuit just naturally has a lot of ripple from the power supply already on it. There's not voltage regulation, there's just Zeners that derive the rails. So as you know, that lets all the ripple through basically. The input filtering, some circuits have just got one capacitor filtering the rail from the bulk caps. Others have got a cap feeding into a resistor into another cap, so a 2-stage RC filter. None of the filters have got high frequency suppression on them. It's all just bulk electrolytic, except for literally these 2 references here have got these tantalum caps on them. Everything else had nothing, or just had 10 nanos, and now it's just got electrodes and 0.1s. So what I was thinking is, because the more, here's the thing, right? The more you load the supply down, the more the ripple is going to increase on the power rails, which means the op amps that are powered from the Zener rails are going to see more ripple. So I'm going to upsize the electrolytic capacitors on all the rails. From like the 4.7s, I'll make them 47s, and the 2 10s. So these are 4.7s for single op amps. I'll make all the 4.7s 47s, and the 10s I'm using for the dual op amps, I'll put 100. So I'll go 47, 47, 100, 100. Oops. 47, 47. I'll take out the 0.1s and I'll put 1s. 1 microfarad monolithic capacitors. Because the frequency response and the ESR on those is really, really broad and really, really low in terms of ESR. 0.1s are good for decoupling op amps, but if they are on noisy power rails and have got spikes and stuff going on their inputs. Sometimes they can actually go into oscillation with these. The one mics are sort of better for that. So I'm going to stiffen up all the rails, like I said, with bigger bulk caps and bigger high frequency suppression caps. And the voltage references I've got, like I said, the Zener supplies that go to them, they've got no smoothing. It's just the 4.7, is it 4.7 I used? Yeah, 4.7 microfarad cap on the VREF. I'll be adding 1 microfarad MKTs in parallel to that, and on the output of the Zeners, there's Zeners going to a resistor going to that. So on the other side of the resistor, I'll be adding on the output of the Zeners some bulk smoothing also, and some high frequency suppression. So I'll go away and I'll add all of that, and then I'll come back and then we'll go start scoping everything out. Because to be honest with you, once the power rails are more solid and there's less stuff that's present, there's going to be less stuff to knock out. So I'm just going to do that first. But with that being said, now I am signing off, and I'll see you guys in the next one. Just don't be surprised when there's a few extra caps or bigger caps and a couple of snubbers. You know what they are now. See you soon. Okay, I feel like a big dummy now. Oh, man, I can't sleep. I went and had something to eat, had a cup of coffee, and I was sitting there thinking, and I came back in to read the data sheet. You know when you're just looking for something specifically and your brain just ignores everything else? I didn't even realize this, but large signal voltage gain, it's also down here too, specified VCC/VE plus minus 15 volts, voltage out plus minus 10 volts, RL, your load, above 2 kiloohms. And we see minimum 15 volts a millivolt, which is a lot smaller than the figure I was looking at, 160, minimum 25. So I guess it would still be fairly up there, given that that's a minimum of 15 and the minimum here is 25, but the typical is 160. So I don't know, it's probably somewhere around, 80, 90, 100. I'm just guessing. But at least I still have a ballpark figure that I can convert to decibels, and then I can work out what the actual open loop gain is in a figure that's the same for both data sheets, i.e. decibels or volts, millivolt. I don't care what it's in, as long as it's just the same figure and I can compare the two. That's what I'm looking for. Alright, I'm off now. That dawned on me. I just thought I'd just add it to the video. I thought, geez, everyone probably noticed that on the data sheet and thought I was blind or something. No, it's just because I was just looking for this AOL and open loop voltage gain. I was also looking for DC voltage gain, and I wasn't thinking about large signal. There's too much different terminology for the same things. But yeah, it's not good to get tunnel vision. Anyways, this time I am not coming back in here. I'm done for the night. It is actually a ridiculous time. It's 4 o'clock in the morning. My sleeping patterns have gotten screwed up the last 2 days because I've been sleeping all day because I've had jaw pain. And then I've been up most of the night. And tonight I wanted to go to sleep at like 1, but it's not happening. So I'm finally getting tired now, so I'm going to go crash. Anyways, take care everybody, and I'll see you tomorrow.